I changed the title a little bit and write submonoid. I will explain why. Okay. The questions are welcome at any time. Interrupt me and ask the questions, no problem. Thank you. Here is the list of titles, what I am going to talk about. First, I will start with introduction and motivation. Then I will explain what is Lie group and submonoid. Then I will explain convolution equations on Lie groups and introduce the spaces which are suitable for such equations. That are generic Bessel potential spaces. Then I will explain what is the convolutions on submonoids and how we can investigate those equations. And then I will show you three examples from practical examples from mathematical physics, which can be solved with these methods. That's a Prandtl equation, Tricomi equation, the Lavrentiev-Bitsadze equation. There's some references, of course. Okay, let me start with the introduction and motivation. I think everybody knows and meets somewhere, and many times perhaps, what is the convolution equation on the real axis. That's the equation when the kernel depends on the difference of arguments. These equations are very important, and especially important are their counterparts on the half-axis, which are known as Wiener-Hopf equations. Sorry, there is some problem, small problem. Just a moment. Yes. On the half-axis, when the integration is from 0 to infinity, not from minus infinity, but from 0 to infinity, and the kernel again depends on the difference of arguments. And there is an analog of these equations on the half-axis. It's Mellin convolution equations, when the kernel depends not on difference, but on ratio of arguments, kx over y. And here the measure is dy divided by y, and its counterpart on the half-axis, you have when the integration is from 0 to 1. Those equations also we meet in Craig problems and so on and so on. Wiener-Hopf equations and Wiener-Hopf technique we encounter in a wide range of disciplines, including, I bring here the list of disciplines where these equations appear. So you see that there are many disciplines where you meet this equation. It's astrophysics and Levy processes, hydrodynamics, X-ray tomography, and so on. A lot of. Not all of them are listed here also. Main tools of investigation are the Fourier transformation and the factorization of complex valued functions. These equations are studied thoroughly by many authors, and thousands of papers and tens of monographs are written dedicated to this subject. What are the main features of equations which I showed you 1,1 and 1,4? Equation 1,1 is a convolution on the Lie group R, where the group operation is just sum plus. And the equation 1,2, that's on half-axis, it's a convolution on the submonoid. Equation 1,3, you remember, Mellin convolution equation? It's a convolution on the Lie group R plus, half-axis, where the group operation is multiplication. And the monoid here is, equation on monoids is 1,4, and the submonoid is interval 0, 1. And now I will, well, perhaps many of you know this, but let me remind you this trivial definition from algebra. What is the group and what is the monoid and submonoid? Lie group is a manifold with the continuous binary operation. When for a pair of elements we how to say, for pair of elements, we have one element, and those, well, as a result of this group operation, and also this group has identity element, which operation with other elements changes nothing. Multiplication gives again this element. And also all elements of the group have inverses. All elements have inverses. And if we have such object group, then we automatically have the following very important properties of this group. First of all, we have Haar measure. Haar measure is defined uniquely on the group. The Fourier transformation, which is surprising, we require not very much from the group, and we have suddenly the Fourier transformation, which is assigned to this group. Fourier transformation, which transforms Schwarz space to Schwarz space on this group. That means fast decaying functions. And it has also inverse and so on. We have convolution equation. Since we have the Fourier transformation, we have convolution equation, which is defined as usual as the Fourier transformation multiplied by certain function, which is called symbol, and the inverse Fourier transformation. This is convolution. And it transforms the Schwarz space of fast decaying functions to the Schwarz space of distributions, if the symbol is from Schwarz space of distributions. And we have generic differential operators, which means that we have differential operators which are convolutions, and they belong to the Lie group. Lie group to every Lie algebra has assigned Lie group. And Lie group consists of vector fields. And since we have vector fields, that means that we have differential operators defined by these vector fields. And surprisingly, these differential operators defined by these vector fields from the Lie algebra are convolution operators again. They are represented as the Fourier transform multiplied by symbol and inverse Fourier transform. So this is very interesting object, Lie group. Now what is this submonoid? First of all, monoid. Monoid is the same as the group, but we don't require, first of all, it's not manifold, and not every element has inverse. The inverse is not necessary. Well, these two properties are missing, and then we don't have no Fourier transform, no Haar measure, and so on. It's not interesting for us, which are interested in analysis. It's interesting maybe for the algebra, people from algebra, but not for us. That's why, to make it interesting, I will work with submonoid. What does it mean? Submonoid is the monoid, but it is a subset of some Lie group. It's subset of some Lie group. And the operation is same in these Lie groups. Well, missing inverse element. Now we have inverse element in our submonoid, but this inverse does not belong to monoid. It belongs to the larger Lie group. But it exists. A Fourier transformation exists now, since it is subset of Lie group. And Haar measure also exists, since it is a subset of Lie group. So we have this structure of analysis on our submonoid. That's why not monoid, but submonoid is important for us. Okay, examples. Semi-closed infinite half axis, zero infinity, but closed at zero. It's a submonoid of the real axis. And here the binary operation is again the sum, and the neutral element or identity, how you want to call it, it's zero again, zero. Semi-closed from the right, 0, 1, interval 0, 1, which is closed at 1. 1 belongs to this set. It is a submonoid of R plus, half axis, submonoid of this group. And this binary operation, here is the multiplication. Identity is 1. So it's two examples of submonoid. And the third example, which is most interesting for us because these first two Lie groups and the submonoid, they are thoroughly investigated. But what the third example, it said something new, semi-closed interval, but now not closed at 1, but closed at 0, 0, 1 interval. It's subset of minus 1, 1. Minus 1, 1 is a Lie group with this operation which you see here, which is not multiplication, not sum. It's some combination, a plus b divided 1 plus ab. It's a group, minus 1, 1 is a group with respect to this operation. And this interval closed at 0, 1, closed at 0. It is submonoid of this Lie group. There exists plenty of other Lie groups. Any star-shaped domain, it's surprising, but any star-shaped domain can be redefined as a Lie group. And you can find there the submonoids, many kind of submonoids. Cones, pyramidas, Heisenberg group, direct product of any of those mentioned Lie groups. They are Lie groups, and the submonoids, of course, can be found there, many different. For the Fourier transformation on a Lie group holds the Parseval's identity. As for usual Fourier transform, here also we have this Parseval identity, that the Fourier transformation maps L2 on the Lie group. We have here Haar measure, so we can define any LP space, but L2 space is mapped by Fourier transformation isometrically and isomorphic to itself. It's isometric isomorphism. And it has the inverse Fourier transform in all groups. And yeah, where it maps to L2 on the dual group, which is the group of characters, We consider Lie groups such that there exists a global group diffeomorphism from our group to Rn. And this then, consequence of this is that the dual group is isomorphic to Rn, So this is the consequence of our how to say admissions, that we admitted that it's isomorphic to Rn. The Schwarz space and the dual space of distributions represent the pullback spaces of fast decaying smooth functions and space of distributions, Schwarz distributions. So pullback, it means you can map, you can replant the functions from the Rn to our group, since we have the isomorphism. It's written here with omega star. You can define any of these functions also on the group, as in on Rn. Okay. Then we have also property as in the usual for usual Fourier transform. The Fourier transform under our admission that it is isomorphic, group is isomorphic to Rn. The Fourier transform maps Schwarz space on the group to the Schwarz space on the dual group. And the Schwarz space of distribution is mapped to the Schwarz space of distributions on the dual group. And for the inverse Fourier transform, the same. It maps again inverse, of course, Schwarz space on the dual group to the Schwarz space on the group. There we have that's why if we take now the function which is distribution on the dual space, in our case it's on distribution on Rn, then we can define correctly the convolution operator this way. We take Fourier transform of function which maps S to S, I mean Schwarz space to Schwarz space, then multiply it by distribution, which is symbol. Now we are in distributional space. And then take the inverse Fourier transform, which brings this distributional space on the dual group to the distributional space on the distributional space on the group. Thus, this operation, convolution, maps Schwarz space on the group to the distributional Schwarz space on the group. The convolution operator is such. This convolution operator has the properties that the composition of two different convolution operators is again a convolution operator, but with one condition, that the product of symbols A, B should be in distributional space. It's not trivial, not always true. But if it holds, then we have this composition property. Okay. If it is a usual function, then it holds automatically. We say that A belongs to the multiplier class on the dual group, multiplier class P, MP, on the dual group if the convolution operator maps LP space to LP space on the group. As usual, multiplier in the case of classical Fourier transforms. So multipliers are defined, LP multipliers, and now we can formulate the theorem. LP here is this theorem says which kind of functions belong to this multiplier class. LP multiplier algebra contains functions of the Wiener algebra. A Wiener algebra is subset of our multiplier class for any P, and the Wiener algebra is we take function from L1, absolutely integrable function, take the Fourier transform at constants. This is Wiener algebra, and they all belong to multiplier class for any P. For P is equal to, the class is described trivially. Multiplier class 2, it just coincides with bounded functions, essentially bounded functions, L infinity G, as it for the case of classical Fourier transforms. Important class of subset of the multipliers are the functions PCP. PCP we call the functions which are closure of PC functions, piecewise continuous functions. That's acronym of piecewise continuums. Piecewise continuum functions closed in the norm of the multiplier class. What is the piecewise continuous functions on Rn? Well, how we understand it? It is it is piecewise, it was piecewise constant on polytopes. Which is polytope? What is polytope? Polytope is the intersection of finite number of half spaces. Here is shown some uh, drawings of polytopes in R3. R3. Parallelepipeds and cubes and so on, they are all polytopes. If we take finite number of polytopes and take functions which are constant on each such polytopes, it's piecewise constant functions. And then we close it in the norm of MP, multiplier class. It's important class for us. Theorem now. That's one more class which belongs to the multiplier class. It's Michelin-Hermander-Lizorkin theorem, which says that if the derivative of functions dxc alpha multiplied by c in power alpha, they are bounded, then these functions are multipliers, LP multiplier for all p. And here is the norm estimate also in this case. It's classical theorem of Michelin and Hermander and Lizorkin. To the Lie group is associated Lie algebra of vector fields, as I mentioned already. We generate generic differential operators, GDOs, acronym in short. Generic differential operators are convolutions. It's written here, you see, with the symbol IXK. DK is operator with symbol minus IXK. And they are generic differential operators. And I will show you that the generic differential operators for different Lie groups they are different. For the generic differential operator for the classical group R, I mean on the axis, it's classical derivative, just classical derivative on Rn. You take partial derivatives. They are generic for this Lie group. For the half axis, the generic differential operator is derivative multiplied by the independent variable, t d dt. And generic differential operator for the group minus 1, 1. It is 1 minus x squared d dx. So they are very different, these generic differential operators for different groups. So there arises a question. So we have now convolution operators, we have generic differential operators, and we organize such a equation where we have convolution on the Lie group. Convolution is x multiplied by y, a group operation of y minus 1. And then also differential operators participating, they are also convolutions. So all in all, this operator is actually convolution operator, but written in this form. This convolution operator has this symbol, which is written here. Differential operators have symbol minus IXC, and the differential and the convolution operators have the Fourier transform of the kernel is this symbol. So we have now differential operators and the in the case of Lie group on R, we know that the suitable space for the investigation of such integro-differential operator is the classical Bessel potential space. But it's not suitable for the Lie groups, for different Lie groups. For the different Lie groups, we have the same definition as for classical Bessel potential space, absolutely the same definition. We just replace classical Fourier transform by generic Fourier transform on the Lie group. How it is done? You take function, you take this convolution operator W with xi in power s. Xi in power s is written here. What is it? Or you take Fourier transform, multiply by this function, take inverse Fourier transform. It belongs to LP space. Then it is generic Bessel potential space for the given Lie group. Given Lie group. And what is interesting, Sobolev space, generic Sobolev space, which is defined as the derivatives up to order m, should belong to the LP space. It is generic Sobolev space to WPM. And this generic Sobolev space coincides with the generic Bessel potential space for the integer m. If S is equal m, then the generic Bessel potential space coincides with the generic Sobolev space, just as in the case of the classical Fourier transforms. The convolution operator is bounded in the generic Bessel potential space. If the symbol is of order R, then it maps generic S, generic Bessel potential space S to generic Bessel potential S minus R. So we have now the mapping property, and now we can formulate the lemma. The multiplier class for the Bessel potential space, generic Bessel potential space, is independent on S. If it is bounded in LP, then it is bounded in all Bessel potential spaces. Again, as it in the case of classical Bessel potential space. So we have no problems with multipliers, because if we have the theorems on multipliers in LP, we have it in all generic Bessel potential spaces. Convolution integro-differential operator with this symbol, with this symbol which is of order m, is Fredholm in the space setting when we look for the solution in generic Bessel potential S, and the right-hand side is generic Bessel potential S minus R, is Fredholm if only the symbol is elliptic, if only. Not if and only if. If it is elliptic. Elliptic means it does not disappear after multiplication by xi by power minus m. Then it becomes bounded symbol. We continue the theorem. Moreover, if A belongs to PCP, that's here you see why PCP is important for us. The ellipticity is sufficient condition also for the invertibility of operator. So we have necessary and sufficient condition for functions which are in PCP class. And the inverse operator to it is just you take inverse of the symbol, which is elliptic, and the convolution operator with the inverse symbol is the inverse operator to the original convolution operator. So here the theory of convolution equations is very simple. If symbol is elliptic, then equation is uniquely solvable, and you have the inverse operator. As for classical convolution operators on Rn, not only on R, but also on Rn. But there is some gap between necessary and sufficient condition, and that has the motivation, because I call it Igari paradox. Igari, he is Japanese mathematician. He proved in '69 that there is very interesting property that if P is not equal to, then there exist continuous functions which are multipliers, LP multipliers, but they are also elliptic, but the inverse is not multiplier. There is surprising example and unexpected, but it is so. And that's why this gap between necessary and sufficient conditions in the previous theorem, it's motivated, and there exist counterexamples for that from by Igari. And okay, now about submonoids. When we consider submonoids, and now we will define the convolution equations on the submonoids as will be analog of the Wiener-Hopf equations of the half-axis, the theory of such equations becomes much more interesting and much more complicated, much more, because it's not anymore so trivial, this theorem about Fredholm properties and so on. It's not trivial, really. Okay, first of all, we define the equation on submonoid, convolution equation on submonoid. For this we take operator Rm, which is the restriction of functions from the group to the submonoid. It restricts function from group to submonoid. Then we take Lm, which extends function from submonoids to the Lie group by zero. It just continues it by zero. So now let us define the convolution operator as convolution where we take the restricted functions which are extended by zero, then apply the convolution, then apply the restriction. Now this operator acts on the submonoid, on the space on submonoid. And yes, for this now we need the spaces, two spaces defined for the submonoid. First space is just restriction of the space from the group to submonoids. Just cut off functions from the group to submonoids. Then it's just generic Bessel potential space on the submonoid. And the another one, another GS with tilde, it is just that functions which are supported only on M, inside M. And then you can continue it with zero. It is subset of the Bessel potential space on the whole group, but it is GS tilde. Functions which have supports on, well, the norms are introduced here as in the case of classical Bessel potential spaces. And now we have theorem about boundedness. Oh, should I? Yes. If we take P between 1 and infinity, the operator on this submonoid, convolution operator on submonoid maps Bessel potential with tilde to Bessel potential with non-tilde, S minus R, is bounded if and only if the symbol is multiplier of order R. So we have no problem again about boundedness. Or if it is bounded on the submonoid, it is bounded in the group. Corresponding operator is bounded on the group, and vice versa. If the convolution operator on the group is bounded, then the same operator on the submonoid is also bounded. Convolution operator on the submonoid is also bounded. Okay. Further, we will dwell on the submonoid on interval 0, 1. And I remind you, the group operation here is this one, A plus B divided by 1 plus AB. This is the group operation. And the generic differential operator, as I mentioned already, is here, second one. Generic differential operator is, oh, sorry, 1 minus x squared dx. And the Haar measure is the x divided 1 minus x squared. That's the operators for this subgroup, for the group 0, 1, minus 1, 1. And Fourier transform here for this group is written here. They are Fourier transform, it's inverse. We have also, as I mentioned, the Parseval identity for them, and so on. But now the first difference. Convolution operator, composition of convolution operator is not convolution again for all symbols. Convolution of on the submonoids is a convolution on submonoids. Composition of convolutions on submonoids is a convolution on submonoids. If either the symbol A has analytic extension in the upper half plane, or symbol B has analytic extension in the lower half plane. Not always. For the convolutions on the groups, it was always true, but here not. Here only this under these conditions. And now our goal is to investigate this convolution equation is same as for the group, but now on the monoid. So the convolution is from 0 to 1, and the convolution operator again on our group, and generic differential operators also. All are present here. The symbol, oh, it jumps. The symbol is written here. So this equation has symbols, and we will consider it in this setting when the solution will look in tilde space, and the right-hand side belongs to non-tilde space. So everything is correctly formulated. We will see that the equation are much more complicated to investigate in one-dimensional case than integro-differential convolution equations on Lie groups, even on multidimensional case. Here, one-dimensional case is more complicated than the multidimensional case, because as you remember, on the Lie group, the theory was very simple. If the symbol was elliptic and from PCP, then we had the inverse operator. Here it's not so. It's much more complicated. And I will explain you the exact conditions. Consider the equation xi minus RA belongs to MP, and consider the convolution equation on submonoid in this setting, which I mentioned. The solution is in HS tilde, and the right-hand side in HS S minus R, HS minus R without tilde. This equation is lifted to the equation in LP space with symbol is written here, lifted symbol is written here. And they are fully equivalent. The equation, original equation and lifted equation. They have even same dimension of kernel, co-kernel. They are Fredholm simultaneously or are not Fredholm at all. They are invertible or non-invertible simultaneously. So it's full equivalence. That's the first step of investigation of this equations, lifting. We lifted it to the space, but pay attention that this lifted symbol is now multiplied by t minus xi minus e, xi plus e, divided xi plus e in power s. And note that if this symbol A was continuous even at infinity and everywhere, this symbol, lifted symbol, is now discontinuous at infinity because of this multiplier in power s. So If we have originally the continuous symbol, lifted symbol is not continuous at infinity anymore. Yes. Um, we will see that just ellipticity is not enough for the symbol to be Fredholm. And here is the definition of the so-called amended symbol. Uh, Amended symbol is such an object. You leave this symbol at points where it is continuous. Same as R psi. It's, I mean, lifted symbol. But if it has discontinuity, we connect it with this function, which is written here. At infinity and at finite points, they are connected with these functions. Let me show you what does it mean. What does it mean graphically? Here is, I draw this symbol in black line. It's the image of this symbol. But this symbol might have discontinuities, jumps at finite point and also at infinity. Here on the left side, you see the jumps is shown jump at infinity. And the others are jumps at finite points. What we do here, we just connect them with certain arcs, certain arcs, these discontinuous points, and make this function, now the image of this function on the complex plane, make it continuous. And the connection is with the arcs, as I told you. From these arcs, this interval between ck minus 0 and ck plus 0 is seen under the angle 2p divided by p. And it's you see here how they are connected. When p is equal to, connection is just with a straight line. In other cases, when p is more than 2 or less or 2, they are connected with arcs, but on different sides. You see. So in this way, we can make symbol continuous. Maybe some of you remember such procedure for singular integral equations with discontinuous symbols in LP, which is due to Wiedom, Gochberg, and Krupnik. They define such a symbol, especially Gochberg and Krupnik, such amended symbol for singular integral operators. And then later, I also define such an amended symbol for convolution equations and Toeplitz operators in my works, and made this amended symbol, define this amended symbol. Why we need, for what we need this amended symbol? This answer will be given in the next slide. The amended symbol, if the amended symbol is elliptic, that means that this curve, now amended curve, does not crosses 0. Then we can define the index. It is, how to say, complex plane, the winding number of this curve, winding number on the complex plane, divided by winding number is index of this function. As usual, index of continuous function in the which is well-known definition. Now we amended symbol make it continuous, image is continuous, and we can define the amended symbol, the index for the amended symbol. Or it is increment of argument when we run around this curve and divided by 2p. So this is defined if if this amended curve does not cross a 0, definition is correct. And now the theorem. P is between 1 and infinity, a convolution operator in the generic Bessel potential space with the matrix symbol is Fredholm only if the amended symbol is elliptic. It's necessary condition. If symbol is PCP, PCPR of order L, the ellipticity of the amended symbol is necessary and sufficient for the equation to be Fredholm. If equation is Fredholm, the index of the operator is non-trivial and is equal to minus index of the amended symbol. It's just the same as for the classical Wiener-Hopf operators. Yeah. Moreover, if I is a scalar symbol, then I don't want now to speak about factorization, so I will consider the scalar case only. I mean, when we have one equation, not the system, but one equation. Then, if index is zero, then the equation has unique solution in the setting which we formulated. If the index is negative, then equation has solution for any right-hand side, but the homogeneous equation, W phi is equal 0, homogeneous equation, has exactly minus kappa solution. If index is, so that means that the solution is not unique. If index is more than 0, which is orthogonal to the solution of the dual the solvability, you have to check if the right-hand side is orthogonal to those solutions. Well, everything is as in the classical Wiener-Hopf equations, but with amended symbols and with the correction that we are now on the groups and the submonoids. Corollary, the image of the amended symbol on the complex plane coincides with the essential spectrum of the operator. I mean, if the symbol becomes 0, the operator cannot be Fredholm. And the spectra can be also defined. It includes also the domains inside this curve where the index is not 0. Then it belongs to the spectrum. Spectra and the essential spectrum is described completely in this case. Now I will mention here several assertions which have independent interest also, but which will play an important role in the proof of the above theorem. First of all, the equation, convolution equation on the submonoid or the dual equation in the dual space, one of them has always 0 solution only. Either one equation or the dual equation have 0 solution. Kernel is empty. That's for the usual convolution equation. Wiener-Hopf equation was proved by Coburn in L2, but then it was generalized. And now it holds also for the group. Well, the composition of the symbol, composition of convolution operators on submonoids minus convolution of the product with the symbol of product, it is compact operator if they have non, how to say, non if they have disjoint discontinuous points, if they have not the same discontinuities A and B, then this operator is compact. You remember, for the convolution operators, it is just zero on the group. But here, you need that these symbols should not have the common discontinuity points. Then this is compact, not zero, but compact. But the commutant, I mean, WA multiplied by composition with WB minus WB composition with WA is compact always for all PCP symbols. That means that the factor algebra of convolutions on submonoids factored by compact operators is commutative algebra. And what is the last one? Yes. No, well, it's a particular case. Well, uh, for the scalar symbol elliptic has trivial index, then the operator is invertible. It's a particular case, but the main theorem was based on this theorem. And now about three examples which I promised. First of them is the Prandtl equation. Prandtl equation is original Prandtl equation is from -1 to 1. And it was surprising that it turned out to be convolution equation on the -1, 1. So the solution was written immediately. Solution to this equation was immediately. But now let us consider the convolution equation of Prandtl on the interval 0, 1. What happens here? In this case, the setting is here. The equation we have to multiply by 1 minus x squared. This equation, it becomes convolution on submonoid. And here is written the amended symbol. Amended symbol. It's non-trivial now. Amended symbol, we have to connect it at infinity. This symbol itself has discontinuity at infinity, and especially after lifting, it becomes, even it was continuous from the beginning, now it becomes discontinuous. So we need this amending this symbol, and the amended symbol is written. And we have this full theorem then. This operator is Fredholm if and only if the amended symbol is not zero. Then the index is written here. It's index of this amended symbol, and it is either 0 or plus and minus 1, only these three cases. And if the symbol is 0, the equation is solvable. If the symbol is -1, then it's again solvable, but not unique solution. If index is 1, then it is solvable only for those right-hand sides which are orthogonal to the right-hand, to the solution of the dual homogeneous equation. As a standard theorem here formulated for this now precisely written symbol for the Prandtl equation. Same investigation is true for the Tricomi equation. Tricomi equation comes from partial differential equations when the type of equation changes from elliptic to hyperbolic, and well, then we have this boundary integral equation of Tricomi derived almost 100 years ago, and nobody can solve it exactly until Petrov. Petrov was first, the mathematician from St. Petersburg, but he did not notice that it was result that this -1, 1 was a group. Then I noticed that it was the group and the convolution operators on the group well, I adjusted this theory here, and it was solved. Now on the half axis, on the submonoid, we again define the uh, amended symbol. It's written here, amended symbol on the lower um, line, amended symbol, and again this same theorem. If this operator is equation is Fredholm, if and only if the symbol is elliptic, and if symbol is elliptic, the index of operator is equals to the index of the function. It is 0, +1, or -1. And again, if symbol, if index is 0, then it's uniquely solvable, and so on. All this holds here also. And the third equation is Laurentiev-Bitsatze equation, which originates from, again, as a boundary integral equation for mixed type boundary value problem for the mixed type differential equation. And again, here we have um, well, first of all, we have to reduce it from half to 1 to -1 to 0, 1 interval to the submonoid. And then after this reduction, we write this symbol, amended symbol, and we get the theorem that it is Fredholm if and only if the amended symbol is not 0. And then the index is index of function, amended symbol, and again it's 0, plus and -1. And the solvability property is also displayed here. It's very similar what was exposed before for these previous two equations. And here are some references. Thank you. If you